Let's take a look at an excellent example by J. Devore in the textbook on probability and statistics. I'm looking at the example in that book's chapter 5, number 21. It's a good example of using probability distributions to estimate different kinds of values. So let's just take a look at it. The problem basically gives three values, 80, 100, and 120. Those in the example happen to be prices, but they could be anything. But three different products are sold for $80, $100, and $120. And we're given a probability of those occurrences on a given sale at 20, 30, and 50% respectively. So that's basically the data we're given, and the graph here shows that distribution as a probability distribution for the sale. So the next sale we expect to have. So questions that often arise are, what's the average sale going to be given this distribution for the company? So if we move forward, we can look for the expected value of any of those numbers. We basically take the value in dollars from X, we take the probability of X, and we can calculate very quickly the expected contribution of that item as things go through. And then as we summarize those values, we get the expected value overall. I could have here calculated the expected value by taking the prod sum over these values. I would have gotten the same result. I choose to do it one item at a time. If you're into economics or retail sales, anything of that nature, you might want to know the expected contribution of each of the individual types of items. So what contribution does the $100 item make toward the average sale? What contribution does the 120 items? So these are the expected contributions of those amounts. If you're not doing that kind of economics, you wouldn't need that number, and you could calculate the 106 in this case without having to calculate those values independently. It's either the sum of these expected values or it's the prod sum across this range. You can do it either way, and it's perfectly acceptable statistically. If I want to look at the variation of that data, I need to determine what the basic standard deviation is, or the variance of the data. I would need to explode some data. So if I take two random sales, so the 106 is the expected value of kind of the next sale or the average sale, but I want to see, can I make that data more accurate? Can I apply, for instance, the central limit theorem to getting a more accurate estimate of the data as I go through? So perhaps I'll randomly sample two sales rather than one. So I've got to go out and pick a first sale at random and go out and pick a second sale at random. So what I'm doing is running an experiment of picking two sales at random. And since every item is $80, $100, $120, there are 8 different combinations that I could get from that as I go. So what I've laid out here are the 8 combinations of values that can occur, if I don't overlay them with values, as I go through my different data. So that's just setting up the experiments as I go. At that point, I want to apply the probability for each one of these as I go. So typically the probability of the pair is the product of the original probabilities for those values. So in this case, it's B4 squared because both were $80. In this case, it's the 0.2 times 0.5 because it's $80 and $120. I don't set up any particular Excel functions to do that when I do it. Usually I'm in a big hurry, and visually I can just do that in a couple of seconds. There's nothing fancy going on here other than I typed in the values in the formulas. From there, I can calculate my X bar. My X bar is simply the average of those two values. So if X was a randomly distributed variable, random variable, functions of random variables are random variables. So now X bar is a new random variable that I can now do statistical analyses on and determine an estimate for as I go through. Okay. Another possible random variable in this case is a function of S2, or the variance of the data. If I take the variance is the difference between X bar and the original X value squared summed for the two values as I go through. Now, the symmetry of the mean of two numbers means I didn't have to have a formula for calculating the deviation of the second value, because I know both values are equally distant from the mean. So I calculate my variance here simply by multiplying it by 2. The alternative would have been D8 minus A8 squared plus D8 minus B8 squared. You end up with the same formula either way. But if you have more than 2 in your experiment, you'll have to have a slightly more complicated formula because you won't be able to rely on that symmetry. But I relied on that symmetry here. So now I know the standard deviation of each sample. It's not the standard deviation of all my sales. It's the standard deviation associated with an experiment that draws that particular pair. Okay. Moving on beyond that, then, I'm ready to look at the distribution of the standard deviations. So actually I'm calculating variance, not standard deviation, but you know what I mean. So what I put here are the values that show up in this column. So it's not, even though there are 8 rows in the experiment, there are only 3 distinct values, so I only need 3 values going through here. I can then collect the probability associated with each. So I can take the probability of 0 up here, I can take the probability of 0 here. I'm holding the control key, obviously, and I can select that probability, and I see that they add up to 0.38 as the total. Likewise, I can pick the value at the probability at 800. I can, holding control key, click the value at 800 and see that they add up to 0.2. So I'm able to quickly just simply add up. I'm not building macros or doing anything fancy here. I'm just figuring out what these values are. One of the ways you can validate it to make sure you didn't make any mistakes is check that the values add up to 1 when you're done. If the 3 values in this case didn't add up to 1, I'll know that I somehow miscounted or maybe missed a row as I went through. I can then take the prod sum of those values, multiplying each to get its contribution, to get the total variance of 244. So the expected value of the distribution is 106, and the variance when I take my samples of 2 is 244 as I go through. Lastly, I can also take the distribution of x bar, because x bar is its own new random variable beyond x. So I can repeat my pattern. I can take the distinct values that occurred for x bar, and I can calculate their probabilities, again looking at the table for redundant values. And when I take the prod sum of that value, I get the mean value of the distribution of x bar. So the original 106 was the expected value of x. This 106 is the expected value of x bar, which is its own random variable. So notice as I increase my sample size from 1 to 2, the expected value of the distribution really didn't change. Mu doesn't change. What does change as I go through is that the variance changes pretty dramatically. So if I recalculate the variance on my distribution to get my S bars, that's really just the contribution of that coming through, and recalculate and sum my variance overall, I'll see that the variance of the x bar distribution is only 122. The variance of the x distribution was 244. So with a sample size of 1, I had variance 244. With a sample size of 2, I had a variance of 122. That's to be expected, because when I sample data from my distribution, the variance will be sigma over n. So as I go from 1 sample to 2 sample, I cut my variance in half. So s squared over n is the variance of the sample. We don't typically talk about s squared over n. We usually talk about the standard deviation, which is the square root of that. So s over the square root of n, sigma over square root of n, is the value we end up with going through. So estimating the value of these things is very, very important. The graphs show the difference in the picture, because both of these are graphs. One is the graph of x, the other is the graph of x bar, both random variables. The original distribution is ascending. It happens to have a mean of 106, but you can barely tell that looking at the graph. The second distribution has sample size of 2. The mean is also 106, but you're starting to see a slight curve start to be associated with the data. If I increased my sample size, picked not just 2 sales, but 4 sales, or 6 sales, or 8 sales, or 20 sales, or 100 sales, keep going. The more sales I pick, the larger my n, the smaller the standard deviation of the sample x bar will be. I'll end up with a very narrow, steep graph centered on 106.